So what we're going to talk about today is we're talking about equations of lines in space. And what I want to do is I want to first start out with talking about directions and directions of vectors, because we're going to utilize vectors in order to draw lines. And one of the things that are really important about vectors from the perspective of lines is their directions. Okay? And in fact, we want to be able to kind of characterize a whole grouping of vectors based upon their directions. So you could characterize vectors based upon their magnitudes. You could characterize them based upon their directions. And if they have the same direction and magnitude, then they're actually what we call equivalent vectors. Okay? But what we want to do first is, or what I want to do first, is I want to first talk about two vectors. And those two vectors, they're going to be in the same direction if they're scalar multiples of each other. And I'm going to start out in 2D, and then we'll work towards 3D to kind of represent this. So let's just start out in 2D. And let's say, for example, that I have this vector. And this vector here, okay, we can see that this vector, if you write it in component form, is going to end up being 2, 1. There's 2, 1. Now, if I take another vector, different location, okay, and instead, that new vector is 4, 2. There are two things that you want to notice about 2, 1 and 4, 2. One, that 4, 2 is 2 times 2, 1. That is, that it's a scalar multiple of 2, 1. And then when you look at it geometrically, what should be clear here is that 2, 1 and 4, 2, in fact, are in the same direction, right? They have different magnitudes. 4, 2 is clearly twice as long as 2, 1, but they're in the same direction. Furthermore, if I kind of think about this and I kind of switch my directions, not really switch my direction, but reverse my vector, okay? Say I draw this one here, this vector here, and that vector now is going to be -2, -1. It's also in the same direction, but what's happened is that I've reflected it. I've reflected the vector, all right? So it's now -1 times 2, 1. And for our purposes, it actually is in the same direction, okay? It's just been reflected over the origin, okay? And so essentially that's like multiplying by the scalar of -1. We can also do this with fractions. We can take fractional portions. So for example, if I wanted to do something along these lines, okay, this is now -1, -1/2. And you can see that that is essentially, that's -1/2 times 2, 1. So it's also a scalar multiple. Now, by the way, one thing here, maybe it's not as obvious, but 4, 2 and -2, -1 are also scalar multiples, because 4, 2 equals -2 times -2, -1. Okay? So if, say for example, we could actually say this, we could say that if two vectors, v and w, are scalar multiples of each other, and w and u are scalar multiples of each other, then v and u are also scalar multiples of each other. So basically what we can do is we can kind of group our vectors into groups where every single one of those vectors has the same direction. This actually ends up being very handy when you do things like linear algebra, and it's going to be super handy when we draw the equation for lines. So if we look at this in 3 dimensions, we'll see the same thing actually. Okay, so let's say for example that I have a vector, and the vector will make the vector 1, 3, -1. So 1, 3, -1, so we'll have to have a -1 down here. So 1, and then 3, and then -1. So there's 1, 3, -1, and we'll just anchor that vector at the origin. Okay, so there's our component vector 1, 3, -1. And then let's say, for example, I take now and I multiply by 2. So I take 2 times 1, 3, -1. Okay. And what I get now is I get 2, 6, -2. So I'm going to go 2, I'll go 6, and I'll go -2. So I'll go down 2. And you can kind of see, actually, that these end up being both in the same direction if I actually have them coming through the origin. I know that's not a perfect representation, but that's exactly what's happening. So it actually also works when we talk about things in 3 dimensions. The direction of a vector really has to do with the relationship or the ratio of the values in the vectors Okay, so like for example, if we take the x value versus the y value, so 3 over 1, that actually ends up equaling 6 over 2. Okay? Or if, say, for example, we say take 6 over negative 2, 6 over negative 2, that actually equals 3 over negative 1. So that relationship continues to hold. Or if we took 1 over negative 1, that actually equals 2 over negative 2. Okay? So it's actually the ratio of the components. Essentially, it's the slope of the vector, right, that tells you the direction, which is actually pretty intuitive, right? The slope of the vector determines its direction. And what's going to be kind of cool is that what we're going to do as we're drawing lines for, drawing equations for lines, all right, is that we're actually going to treat the vector that we generate as the slope of the line. You're going to see it's going to like kind of equate to the slope of the line, and that's going to be really valuable. The second point that we want to get here is that the equation of a line in space can be defined using a direction vector and a point to anchor the line in space. This direction vector, remember I just said it's kind of like the slope. It actually is the slope. And if you think about what do you need in 2 dimensions in order to get the equation of a line, you need, one, you're going to need the slope, right? Okay. And you are also going to need basically an intercept. So the point in space is going to end up being your intercept, okay? And the direction vector is going to end up being like the slope of your line. And let's see why this is the case. So let's say, for example, I've got 2 vectors, okay? I got 2 vectors. And let's say, for example, that they're actually equivalent vectors. They're actually located at different points in space. Okay? So there we go. So we've got the same direction vector, right? So equivalent vectors, but actually each one of them starts at a different point in 3-dimensional space. If I want to draw a line, what I'm going to imagine doing is I'm going to actually imagine extending out the line infinitely. Okay? Basically what I'm going to do is I'm going to multiply the vector by a scalar, and it's going to give me a new point. Okay? We multiply the vector by the scalar, give me a new point. You can actually see, in fact, right, that we get a different line, the blue line, than the yellow line, and the only difference between the two of them is where we actually create the initial point for our vector. All right? That's it. And so that essentially that's going to be kind of the idea. The idea that we're going to be working with here is that we'll find a point, okay, and then we're going to take that direction vector and we're going to use that, basically utilize as an anchor. So let's say, for example, that this point here, this point is x naught, y naught, z naught. And let's say that this vector right here, we'll call this vector ABC, and this is v, and we'll actually let it equal, we'll call it A, B, and C. Okay? Now, if I take, right, x naught, x naught, y naught, z naught, and I add to that 1 times a, b, c. Okay? 1 times a, b, c. What you can see is that I'm going to end up right here. Okay? That's my new location. Okay? And you can think that there's a point right there. Okay? There's one point at that point. If I change this scalar, right? If I change the scalar 1, let's say I make it into 2, and now my new location here is way up here because I've stretched the vector by 2, okay? And I've added to it x naught, y naught, z naught. Right? Basically take my... Okay? So now taking x naught, y naught, z naught plus 2 times a, b, c, and I end up at this new point, okay? The second new point. If I wanted to go backwards, I could, just by multiplying by a negative scalar. So this new point right here, okay, is going to be x naught, y naught, z naught plus negative 1 times a, b, c. So what we're essentially going to do is we're actually going to utilize a parameter here for the scalar. We're going to call that parameter t. Okay, we'll call that parameter t, and so as I change t, I end up at a different location along that line. Now, what you want to do is you want to think to yourself, well, there's no way to get off that line. right? Okay, because basically, if I change t, it's just going to take me further out, either forward or backwards along that vector, okay? So as long as I'm anchored, right, essentially with this value here, which is basically an intercept, right? As long as I'm anchored along the line and I'm going in the direction of ABC, I'm going to end up everywhere on that line, or somewhere on that line. And if I think about like the infinite number of values that I can have for t, okay, then I know that I can actually get everywhere on that line. All right? So like for example, if I want to actually get to x naught, y naught, z naught, think to yourself, well, what's the value that I'm going to need there? The value that I'm going to use or I'm going to need there is 0 for t. So x naught, y naught, z naught plus 0 times ABC just puts me at x naught, y naught, z naught. So it makes sense to call that an intercept, right? Plug in 0 for your parameter, and you end up getting just like whatever the value is for that anchoring point or your intercept. So what we have now, or what we're going to construct now, is called the vector equation for our line. So what we're going to do is we're going to say, okay, so we'll generate some new vectors or some new points, all right? And the vector equation for our line is going to be r, okay? That's the line notation, all right? R naught is going to equal, and it's going to be that initial point written as a vector. So it's x naught, y naught, z naught. So it's the initial point written as a vector, and then r naught, right? You should notice that that's the intercept notation that we've utilized so much in calculus and the like. And then v is the direction vector. And we're going to represent that as a, b, and c. So essentially the vector equation for our line, r, the line, is going to equal r naught plus the parameter t times the direction vector v. Okay, and so here's our parameter. Okay, and basically that's our parameter, right? And what we'll get is as a result of this, we get different vectors, right? We're going to get different vectors. Each one's of different lengths, right? But they're all going to be along the same direction, okay? And they're all going to be anchored at that point x naught, y naught, z naught. Next, we're going to take a look at some parametric equations for a line in space. Now, we're going to utilize that vector equation in order to draw these parametrics. So let's say, for example, we have r, and we're going to let r is actually going to be, if you think about it, it's x, y, and z. Okay? So we know that r, our vector equation for the line, r is going to equal r naught plus t times a, b, and c. Okay? Now, in a parametric equation, if you remember, a parametric equation breaks down the equation for a line or whatever that we're looking at in terms of its x and its y. So it relates its x's and y's, and then it relates them in terms of a parameter. So we're going to do the same thing. We've just now got to do it with 3 dimensions. So I'm going to rewrite my vector equation. It's now going to be, right, x, y, and z equals, and we've got the x naught, y naught, and z naught, plus t times a, b, and c. So there's our vector equation. And then what I'm going to do is I'm going to break down the vector equation into x, y, and z, into the x, y, and z components. And that's going to give me my parametric equations. So for example, I've got x is going to equal x naught plus ta, y is going to equal y naught plus ba, and z is going to equal z naught plus ca. And those are our parametric equations. Let's take a look at an example of how we actually might use this. So let's say we have this question. Find the parametric equations of a line passing through 1, 4, -2, and -3, 5, 0. So we've got 2 points, And using those 2 points, we can generate a vector. Let's generate our v vector, our direction vector, v. So v is going to end up equaling -3 minus 1, comma, 5 minus 4, comma, 0 minus -2. That's now going to give me -4, 1, 2. That's my direction vector. Then I can choose either one of these points. Now, the equations for the lines are going to be different, but the line itself is actually going to be exactly the same. No matter which one you choose as your R0, or which one you choose to actually do first in terms of the direction vector. The only thing that's going to change is what the value of the parameter is going to be depending upon which point you want to go to. So, I'm going to select 1, 4, -2. So, my R, my equation, is going to equal, or my vector equation, R is going to equal 1, 4, -2 plus t times -4, 1, 2. And so when I write my parametric equations, I'm going to get x equals 1 minus 4t, right? Because I got 1 minus 4t. Y will equal 4 plus 4t, or excuse me, 4 plus t. And z will end up equaling -2 plus 2t. And those are the parametric equations. Should I choose to use -350, I just get different equations, but it actually turns out to be the same exact line. The only thing that's changed is what parameter that I would use to get to different points on the line. So let's take a look at another form that we can utilize called our symmetric lines, okay, or the equation of a symmetric line. So we're going to take our parameters, and now what we're going to do is we're going to generate a way for us to find x, y, and z. Okay, so to find x, y, and z when we're given just one of the values. So when we're given just x, when we're given just y, or we're given just z. Okay, and basically we just pull these from the parametric. So we'll construct the parametric equation, okay, and then we can create the symmetric lines. What we're going to bank off of here is we're going to bank off of the fact that t is the same for x, y, and z. T is going to be the same for x, y, and z. And so consequently, we're going to solve each one of the equations for t. So if I first start out with my x equation, x minus 1 is going to equal -4t. And so that means that x minus 1 over -4 will equal t. Then y, what we can see is that y minus 4 is going to equal t, just subtracting 4 from both sides. And then we can see that z plus 2 divided by 2. Z plus 2 divided by 2, and that's just the algebra to get to t, is also going to equal t. So we solve all three of them for t, and once we've done that, my symmetric equation for the line is the following. It'll be x minus 1 over -4 equals y minus 4, which equals z plus 2 over 2. And so how this works is something like this. Let's suppose that we let x equal 0. If we let x equal 0, then we see that 0 minus 1 over -4 is going to end up equaling 1/4. Okay? Y then is going to be, we need to figure out what y is. All right, so y minus 4 should equal 1/4. And so we add 4 to both sides, we end up with 4 and 1/4, or 17/4. So y equals 17 over 4. Okay? And then z, we're going to see that if we take 1/4, we get z equals, excuse me, not z, we get 1/4 equals z plus 2 over 2. And so consequently that means that 2 equals 4 times z plus 2, just cross multiplying. And so 2 equals 4z plus 2, okay, or plus 8, excuse me, plus 8. Subtract 8 from both sides. We end up with that 4z equals -6, so z equals -6/4 or -3/2. And so if we allow x to equal 0, we can now find y and z, okay, just by plugging in that value for x and then utilizing the symmetric equations. You can actually see that that would be the case too, although if we utilize the parametric equations, we'd have to use the same t. We'd have to figure out what t is. So for example, if I went in here and I said, okay, well, let's see if I can find that point. We saw that x, okay, we saw that this value here, we got that value for t was equal to 1/4. So if t was equal to 1/4, right, because that's the value we got with x minus 1 over -4, then x would equal 1 minus 4 times 1/4. And that's coming here from the parametric equation. And that equals 0. Then we take y, the parametric equation, and y equals 4 plus 1/4, and that's going to equal 17/4. And then z is going to equal -2 plus 2 times 1/4, which equals -2 plus 1/2, which equals -3/2. And so you ended up with the same exact values for our parametric as we did for our symmetric. Okay? So basically, what this is this is going to end up giving us a different way of finding the values for x, y, and z, depending upon, basically what we're given or what might be easiest for us. Sometimes also, this is going to come in kind of handy when we do some proof. Let's take a look at another example. So let's take this example. Let's say we want to find the parametric and the symmetric equations of the line passing through 1, -3, 2, and 5, -2, 8. So what we're going to need first, right, we're going to need the vector equation, because that vector equation is going to make it very easy for us to work. So what I'll do first is I'll find v, my direction vector, and v is going to end up being, right, 5 minus 1, comma, -2 minus -3. And all I'm doing is I'm doing this component-wise. 5 minus 1, -2 minus -3, and 8 minus 2. And so that ends up being 4, 1, 6. Let's just check that. 5 minus 1 is 4. -2 minus a -3 is 1. And 8 minus 2 is 6. Great. So that's a direction vector. And so my vector r that I've got here is going to end up being 1, -3, 2. And you can actually choose either one of the vectors you want. Plus t times 4, 1, 6. My parametric equations should be pretty simple to set up. They should be x equals 1 plus 4t, y equals -3 plus t, z equals 2 plus 6t. And so there's my parametric. In order to find my symmetric, what I'm going to do is I'm going to solve each one of my parametric equations for t. Okay, so we'll solve for t. And so that gives me then x minus 1 divided by 4 equals t, y plus 3 equals t, and z minus 2 divided by 6 equals t. So my symmetric equations, when I write these out, they are going to be x minus 4 over 4 equals y plus 3, which equals z minus 2 divided by 6. And those are my symmetric equations. So what we've looked at here now is we've looked at 3 different ways to represent a line utilizing vectors. Okay, these are going to be really crucial for us as we continue to work. And you want to kind of like just get very used to like writing things as equations, thinking about vectors as directions, okay, and thinking about them anchored utilizing points. Let's suppose that we want to find the vector equation of a line segment. So in this case, we're not really interested in finding the entirety of the line, which is really handy and very important, probably more important than finding the length segment, but we just want to know a particular segment. We just want to know a little point. And so let's say, for example, we start at point P, and we end at point Q, and we want to create an equation for the line segment between P and Q. So that's our job here. And let's say that P is going to be given by the vector x naught, y naught, z naught. Okay? And we're just arbitrarily choosing that for our x naught, y naught, z naught. We could choose Q to be the same thing. And then we'll have x be, or Q be x1, x2, x3, that vector there. Okay? If we actually construct the vector equation, it's going to be R equals, and we'll have it be x naught, y naught, z naught, and then plus t, our parameter, times, and we'll do what we just did before, right? We'll take x1 minus x naught plus, not plus, but comma y1 minus y naught, comma y2, comma z1 minus z naught, right? So we're just going to subtract component y's in order to get the direction vector. So what that gives me, if I kind of break it up, is that I'm going to get R equals, and I've got x naught, y naught, z naught, plus t, and it's going to be t times, and it'll be these vectors, it'll be x1, y1, z1, minus x naught, y naught, z naught, right? Because that's how we add and subtract vectors. And so R then, we can rewrite this as R is going to equal, we've got x naught, y naught, z naught, minus t times x naught, y naught, z naught, plus t times x1, y1, z1. And if I just go in and I factor out my scalars, this is a 1 in front of here, so I end up with 1 minus t times x naught, y naught, z naught, plus t times x1, y1, z1. We'll call this vector Q. It's the vector that goes from the origin, basically the component vector that goes from the origin out to our point Q. We'll call this vector P. And so our equation for the line segment is going to be 1 minus t times that vector P plus Q, or TQ, where we've got the parameter t. Now we only want this line segment, so we only want the points in between here and here. So what we can do here is just to notice this. If I plug in 0, right, if I let t equal 0, then what I get is I get 1 minus 0 times p plus 0 times q. And what is that? That's just p. So that ends up giving me that end of the line segment. If on the other hand I let t equal 1, then what I get is I get 1 minus 1 p plus 1 q, and if I add those together I just get q. So that's this thing right here. Okay, there's the 1. That's when t equals 1. So at t equals 0 I get p, and at t equals 1 I get q, and if I want anything else in between I'm just going to pick numbers between 0 and 1. So my vector equation is going to end up being R, we'll call that my vector equation, R will equal 1 minus t times p plus tq, okay? And we're going to restrict from t greater than or equal to 0 and less than or equal to 1. And that way, we're only going to get the segment because we're only going to be picking values in between 0 and 1, and that'll take me somewhere, moving up and down inside of this line. And there's the equation for my line segment. So let's say, for example, that I want to find the parametric equations of the line segment between 2, 1, 4 and 3, negative 1, 3. I'm going to assign P to equal this vector 2, 1, 4. And I'll assign Q to equal 3, negative 1, 3. And then I'm just going to use my equation. R is going to equal 1 minus t times the vector 2, 1, 4 plus t times 3, negative 1, 3. And then I'm just going to do some simplification because I need parametric equations. So this is going to give me 2 minus 2t, 1 minus t. Okay, so all I'm doing is I'm just multiplying 1 minus t times each value in the component. 1 minus t, comma, 4 minus 4t, plus, and then this will be 3t, negative t, 3t. And then I can just combine all of these. So r will again equal, and then this is going to be 2 minus 2t plus 3t. So this is going to be 2 minus t, 1 minus t minus t, which is 1 minus 2t, and then 4 minus t plus 3t, and that's going to end up being 4 minus t. And now what I have is I just have the straight parametric equations. I have x, y, and z. So this is kind of like a different way to go about doing the calculations. I end up with x equals 2 minus t, y equals 1 minus 2t, and z equals 4 minus t. And there are my parametric equations. Pretty simple. It's just a matter of doing some algebra, getting the form correct, and then doing some algebra. Oh, you know what? I made a mistake. This should be 2 plus t. Okay? Because 2 minus 2t plus 3t is actually going to be 2 plus t. But still, same idea. We're going to take r equal to 1 minus t times our vector p plus t times our vector q. And then we're just going to combine our terms. And there we go. All right, so let's actually take this example. We'll find the distance between m, which is 1, 1, 3, and the line x minus 3, 4 over 4, y plus 1 over 2, and z minus 3. So what I'm going to do now is I'm going to imagine I've got this line in space. Okay, I've got this line in space, and I've also got my point m. Okay, and I want to figure out what this distance is, d. So I'm going to need a point here, a point on the line. Okay, I'm also going to need this direction vector v. Right, we'll call this p, we'll call this v. Now the cool thing about p and v is that if I have the vector equation for the line, I'm going to get p and v. Okay, I'm going to get p and v because, right, one point, other point. Now, 1 point and the direction, that actually gives me the whole thing that I want. The thing about it is that in this case, we've got a symmetric equation. So I don't have the vector equation, but the symmetric equation is pretty much in terms of the vector equation anyways. Remember, my symmetric equation is written like this. It's written as x minus x naught over a equals y minus y naught over b, which equals z minus z naught over c. A, b, and c, right, okay, my vector v, my direction vector v is actually a, b, and c. And my point p in this case, right, this guy right here, is going to end up being x naught, y naught, and z naught. It's kind of handy. It's a handy little piece of information to know. Now, if I go and I look at my symmetric equations, 1, v is going to equal, right, this is 4, 2, and 1. So v equals 4, 2, 1. And then p is just going to equal the negative of each one of these numbers. So p is going to be 3, negative 1, 3. 3, negative 1, 3. And there's my p. Pretty simple. Okay? Or that's actually my point p. That's my x naught, y naught. That's my point. So there's v. Now remember our equation for distance. D is going to equal pm crossed with v divided by the magnitude of v. So the magnitude of pm cross v divided by the magnitude of v. I need pm. Well, here's p, here's m. How I create pm is I've just got to go in and subtract the 2 points, right, to create a direction vector. So pm is going to end up equaling, it'll be 3 minus 1, negative 1 minus 1, and 3 minus 3. Right? Just go in and subtract the points. That's what we've been doing in order to find our direction vectors. So this will then equal to negative 2, 0. And that's PM. Now I've got PM, I've got V. All I've got to do is I've got to go in and solve for D. Okay? So I'll first start out by finding PM cross V is 2, negative 2, 0, and V is 4, 2, 1. Those are our two vectors. Negative 2I minus, and this will be minus 2J, okay, and then 2 times 2 is 4, 4 minus 4 times negative 2 is 8, so plus 12K. And that's PM cross V. So the magnitude now of PM cross V is going to equal the square root of negative 2 squared plus negative 2 squared plus 12 squared, which ends up equaling the square root of 152. And then the magnitude of V squared, right, or the magnitude of V, right, we got 421 is going to equal the square root of 4 squared plus 2 squared plus 1 squared, which equals, and that's 16 plus 4, that's equal to root 21. So my distance, plugging it into this equation right here, is going to end up equaling the square root of 152 divided by the square root of 21. And that's how we found the distance between the point and the line. So we actually put in a lot of different things into this particular activity here. One is we recognize that we've got a parallelogram that we're working with here, okay? And that's where our distance formula comes from. Basically, it's our base times our height equals, and in this case, the area of the parallelogram is going to be that the magnitude of the cross product. Then what we need to do is we actually need to generate some different vectors, right? One, we have our direction vector, which we got from the vector equation, which we actually pulled from our symmetric equation in this case. And then the second part is the point that actually is going to be coming from that symmetric equation and creating a vector or a direction vector or a component vector, using the point we're trying to find the distance from and a point on the line. Okay. Once we've done that, what we now need to do is we just basically need to put it into the equation and run the calculation.